So we just decided that a static magnetic field doesn't do any work on a charged particle. But you may remember things from your childhood that suggest otherwise. So we all played with a magnet, and you brought it up to a paper clip, and you picked up the paper clip. It pulled it up, right? And I can sit here and I can feel it pulling. I can feel it doing work. It feels like it's doing work. I have to do work to get it back off. Or we can look at this. This is a current carrying wire. So that's a bunch of particles moving through a metal, a bunch of electrons moving through a metal when we turn on the current. And it's near a small region of a magnetic field created by this horseshoe magnet. So if I turn on the power and the current flows, what's going to happen? Let's see, turn it on. Here's the switch that starts the current, and it jumps up. It jumps up. It wants to go in a circle, but it can't. But even at this point right here, here I am pushing down, and it wants to go up. It's pushing back. It's like it's doing work. So how can that be? We just showed that if V is always perpendicular to F, there can't be any work. So something's going on. Let's see if we can figure it out. So let's see if we can figure this mystery out by considering the force on a wire. All right, so let's imagine what we just saw, a metallic conductor, and it has some current flowing through it that way, and it's in a magnetic field, say pointing into the board. And this time, we want to be real. We want to talk about the actual particle that's moving. It's the electron. And since the electron is a negative particle, it's drifting that way. Its drift velocity for a negative electron is against the current. Current is the flow of positive charge. So here is the electron. So let's think, what's it going to do? Now we said the magnetic field can't do work on a free particle. And the electron is basically free inside the metal. Right? I mean, we described that the way metals are, it's like the electrons are like particles, like a gas. They're free to move around inside the metal. So at first, it'll just do what it's supposed to do. Let's think about the force V cross B. The force is up, but it's an electron. It's negative, so the force is down. So it's going to pull it down like that. And as we've been talking about, it's always going to be perpendicular to the motion. The electron is going to go through a curved route, through a circular path. And what's it going to do? It's going to hit the edge of the wire. Now when the electron is moving at all, it kind of drifts forward because it's always randomly jumping around and losing its momentum in random directions as it jumps around. But now they're all being pushed and they're all losing their momentum, like in the Drude model, by hitting the bottom. So they're pushing on the wire. Okay? So even though we have our electrons moving this way, the force to the wire is always that way, and it's able to end up doing work because the electrons are not free to do what they want to do. If they were truly free particles, they could go in a circle. That's what they want to do. They do part of their circle, and then they're interrupted by having to stay inside the wire. They're no longer free. Okay? So for the force on a wire is due to the motion of the charge carriers. We need a new equation. Oops. For FB. Okay? It's going to be essentially the same, but it actually, in terms of the forces you get and the way it behaves, it's different because those charge carriers are not free. So let's think now about what that force should be. All right, so let's come up with our new formula for the force on a wire. And in this section, whenever I say a wire, it's implied that it carries a current. If the wire weren't carrying a current, we wouldn't be talking about it. It would just be a piece of metal. So wire always means a current carrying wire. So let's draw and think about our microscopic model of conduction. So here's our wire. It's got a current I. And we are going to go back now to the standard notation where the current is carried by positive charge carriers. And of course in a metal it's not. It's carried by negative electrons, but let's just to keep the equation simple, and keep the negative sign simple, we're going to assume it's positive charge carriers with charge q, drift velocity vd, remember they all drift down the wire, and remember we need that number for the density in carriers per unit volume. Remember, that's just the count, that's the number. You have to multiply it by q to get the charge per unit volume. Okay? So let's start with the standard expression, FB, for a free charge. It was q v cross b. Oh, and of course there is a B field present here. So B field sticking into the board. Doesn't really matter the direction right now. Okay? So now what we want to do is apply this force to all the charge carriers in a piece of the wire. Okay? So we make the wire a little bit longer, and let's think about a piece of it. If we grab a little cylindrical section of it, like this, cross-sectional area A and length L. Okay? Let's call it a big L. Length big L. That's a little volume piece of the wire, right? So now, let's see if instead of just Q, we can put all the charges in, not just the single charge. So that would be what? Well, we would need to get all the charges inside this volume. So that volume is equal to A times L. There's your volume. To get the number of carriers, you would multiply that volume times N. N is carriers per unit volume. You multiply it times the volume. That's the total number of carriers. And each one of them has a charge Q. So we put a Q here. So instead of just Q for a single charge, it's QNAL for all the charges. The velocity, they're all moving at VD. And the magnetic field is the same, cross B. So that's how you would represent the force, the total force on the wire for a length L. Okay? Now, let's now think about our microscopic model of charge, or of current. We talked about this before. We have an expression for I, and I don't want to get any of the details wrong. Yes, it's NQ VDA. The charge carriers per unit volume times their charge times their drift velocity times their area. We thought about that in LS5, I think it was. So what we got to see is that most of that is sitting right here, right? NQA, NQA is all right there. So NVD is right there. So we can sort of write this now differently. We can write FB equals I. We can pull the I out. Okay? We pull the I out. That pulls out the N, the Q, the A, and we're actually going to take the magnitude VD out and not make it part of the vector. And we're going to write L as the vector. IL cross B. And that is the force. We have to have that L there to make it come out in newtons. And we write it this way. It's sort of the same. It came from the exact same equation. We just took, instead of one charge, we did a bunch of charges. But we switched this V and this L so that you can really think about the current, right? If we didn't have the V in there, it wouldn't be the current. We want to think in terms of the current. That's the macroscopic property we want to think of. But to get a vector, we just have this L, and L is just the size of the piece of wire you're looking at. So this is just the length of the straight wire, and the direction equals the current direction. Okay, so L. So that's just a vector. Points along the current, has a magnitude equal to the length. Now, not all wires are straight. It's hard to get current to flow in a wire that's straight, that doesn't loop back to a circuit, right? So next we'll think about what to do with a curvy wire. Here's force on a curved wire. All right, so now instead of a straight wire, let's have a very curvy wire. And let me try to draw it nicely. It has a uniform diameter. Like that. Oh, so close, okay. And there's current flowing through this wire. The same current has to flow all the way through the wire, like that. And let's put it in a magnetic field. Doesn't have to be uniform, but I'll draw it uniform just to make it easier to see. All right. If this wire were straight, we would have F on the wire equals IL cross B, like we just talked about. If it were a straight segment, current gives you the direction, the length of the straight segment gives you the magnitude of L. We don't have that. We have a curved wire. So what we have to do is break it into little pieces, right? So if it's curved, and if we look at a small enough piece, like this piece right here, that piece is essentially straight. So this is a differential segment of the wire. And when you hear differential, you know what's coming. We're going to do an integral. But first, let's think about the force on that differential segment that we call ds. Okay? So let's look at a segment of the wire. Well, since it's a little piece, we're just going to figure out a little piece of the force, dF. dF is the differential force on this little segment, ds. Well, let's just copy the equation. I, the current, is the same everywhere. So for L, that's the size and the direction of the current. So we actually call our ds a vector. We draw a little vector like that, ds. And if we were to draw it here, there's ds. And if we were to draw it here, there's ds. So ds just marches along the wire, following the direction of the wire and the current, and always a little differential small piece, so it looks straight. So I ds cross with B, whatever the B field happens to be, wherever you are. Okay? So pretty much the same thing. We just replaced L with ds. So now we just have to integrate. We add up the force on all these little ds's. And you could worry, what if it curves and the force is in the opposite direction? That's okay, because it's a vector. We're adding up all the vector df's. So let's say for a curved wire, then we just integrate to get the total force, FB, and it would be the integral of I ds cross B, and we have to say from where to where. Well, we could sort of start here and go here. If we want to do the whole thing, we could go from A to B. So that's just, those limits are where you follow, from what point on the wire to what other point on the wire. So when you integrate along a line like that, it's called a line integral. It has several other names: contour integral, line integral, whatever you want to call it. And it looks pretty tricky to do this integral, because here's your ds, here's your differential in your integral, and it's a vector, and it's crossed with something else, right? This is vector calculus. It gets pretty ugly. You have to cross your ds with your b to get its contribution to df, and then add them all up, and it's a mess. That's why vector calculus is hard. Just like the vector flux for Gauss's law, though, we're always going to do fairly simple geometries where it won't be that hard to figure out the integral without having to actually do the integral.